Welcome to the second part of a talk talking about power management features. There's way too much power management features, so that's why it's part 2. Part 1 was last year at the LCE, and I hope you've seen it, but it's not a requirement. So who am I? My name is Théo in English, or rather Théo in French. I live in Lyon, which is in France. I won't say where exactly in France. I've joined Butlin for a few years now. I've started with an internship, which I would highly recommend if you are looking for that kind of opportunity. And then I went on to doing driver development on embedded systems. So 2 main projects that I can share with you. We did the initial support for Suspend to RAM on a TI SoC, that is an automotive SoC. That was great. Lots of issues with that because then you get interaction in between the power management features that you don't expect at first. You have a lot of devices to deal with. You have Runtime PM that helps you with that, but sometimes it is not aligned with what you want to do at Suspend. And that's mainly the goal of my part 1 that was last year. So if you want to see more about system-wide Suspend, you should go and see that. And nowadays I work mostly on Mobileye SoCs. Someone from Mobileye is here as well, so if you want to know more about them, feel free to reach out. So we did base support, and we do all of the upstreaming for them so that they get an upstream kernel and benefit from that. I don't need to sell it to people in the room. I've also done quite a bit of pipewire, mostly during my internship. That's great, so a bit of audio background as well. And we do, or try to do everything as open source at Butlin and make it upstream first. So that's a good reason to work on projects. I'm maintaining currently elixir.butlin.com, so you might know the website. It is useful to browse the kernel sources and send links. I'll have a few links in the slides, so you can click on that and you'll get access to the code, source code directly. So what are we talking about? First of all, before saying what I will be talking about, I wanted to clear up who I want to talk to. So my goal is to have driver developers that work on embedded systems. That's who I aimed this talk at. And I want to mainly cover what APIs exist. The APIs I will cover are pretty not advanced, but they are not used by everyone, by every vendor, and maybe they should. I'm not saying they are all perfect, just I want to cover what currently exists inside the kernel, to make sure that if it makes sense, you at least know about it and can think about if it does make sense for your own platform, if it models your hardware well. So that's what we'll be covering this year. We'll be talking about Linux power management, which I'll abbreviate to PM because it's going to be way too long otherwise. I'm going to be out of time. We'll cover Runtime PM features. So we talked about that last year, but I want to cover some more features because there's a lot to cover. It's pretty simple if you start looking into it, but then you get into many quirks. Then I want to cover power domains, which is a broad word for a few features that we have inside the kernel, and again, quite a few things to know about. And then we'll talk about PM, QoS, so quality of service, in this context inside the kernel and what is provided here. The thing I skipped is what we'll start with is how to reason about power management. So it used to be my conclusion of this talk. I wanted to finish by how it is difficult to do power management, but I thought it would be easier to talk about it at first so that you have that in your mind when we talk about every feature. So we'll start with that. So how to reason, so how I see power management in my head. So what it is, the basics is turning off features. You turn it off because it consumes less power. You just disable your hardware that you don't need at some point. It might be for a really long time. When you do Suspend, you disable most of your hardware. Here, in our case, we'll talk about per device disabling of features. That's what it is. Why we care? Well, I don't need to tell you. If you know you care, you care. Mostly batteries, that's the main reason. And how we do it. So I always see it as a line, as a trade-off line in between keeping your resources available all the time, which is great for performance, bandwidth, but isn't great for battery. And on the other side of the scale, you shut down everything, which is great for power, but what it means is that when you need a feature, in the future, you don't know about it, and then someone makes a request for a feature, you need to turn it back on, and that takes quite a bit of latency. So it increases your latency to deal with stuff whenever you need to talk to hardware. And so that's really where the trade-off is. But it's actually a bit more complex than that. We saw the scale that goes from keeping things enabled to turning stuff up, turning stuff down. Actually, you need to think about throttling as well, which is another dimension to think about. That is when you slow down your hardware. So, of course, that's complex. Do you want to what's the optimal position you want to be in? Do you want to always keep it on and then turn it off completely and back on? So do no throttling. Find a middle ground where you do a little bit of throttling. And then you need to know your transition costs from a low speed to a high speed to make the right decisions. But those decisions are really hard to make because they depend on what your hardware looks like, what it can do, what physically takes time to initialize. So we can talk about PLL inits. That's mostly what you expect when you talk about hardware that takes a long time to init. But there's way many other things to think about. I wanted to squeeze in raise to alt. So that's whenever you want to do basically, it means your cost, your latency cost to resume a device is pretty small. And so it means it is much more worth it to slow it down a lot, turn it back full on, and then back down. So it means it's not really worth it to do a compromise on speed. On the other side, you have devices where it does make sense to put it at half speed because the latency, the resume latency is really, really high. But decisions are also project dependent. So you have your hardware and you use it in some embedded domain, and that will define how you want to use your hardware. So the decisions are really hard to make in a generic manner. You can't just say, oh, it's better to turn it off and back on. Yeah, but what if you know you need to wake up every millisecond or every 2 milliseconds? Then, in that case, well, if you know your project, you can make better decisions. So that's a lot of work, sadly, but we won't go around it. You need to think about all of those things. And so whenever we talk about projects, we talk about what's your work like and can you measure it? So you need to start measuring stuff so that you can optimize, well, if it's latency that you want to optimize or power management per amount that is used. Also, you also need to think about, and if you are in that capacity, it's great, can you challenge the design decisions? That can be really helpful. If you are allowed to say, maybe this power domain can be shut off, then you can make great gains. But that needs to go back and forth in between the design and the project aspect. And there's some more issues. That's not enough. So as decisions are really platform and project specific, it's really, really hard to implement a driver that works well for everyone. So whenever you get into pretty complex projects, you will often need to tweak how the code behaves just because it's a different platform and you want different decisions. So the way I see it is that your current state of your hardware is the combination of what's the state of every resource inside your hardware. And of course, every resource can be in different state. It can be reset. You can have a clock that is lowered. You have multiple clocks for each. So that's a lot of states to handle. And you sum that up to make a massive combination that is your current power state. What we often do nowadays inside the kernel is we don't define exactly what something means. So when you say something is runtime suspended, it doesn't make much sense. It doesn't tell you what's the current state of the hardware. I've given an example here, network switch over PCI. What do you mean by runtime suspended? Is the switch available? Is it working fine? Maybe. Is the bus running, the PCI bus running? Maybe, maybe not. So in some projects, you could have your network switch, you want it to turn it on and to stay active, but turn off your PCI bus because that's not needed for your switch to be active. On other cases, your switch requires the PCI clocks, for example, and you need to keep that enabled. So really, runtime suspended doesn't mean much. but that's really helpful, right? It would be great to be able to model everything perfectly and say, oh, this is in runtime suspended, it means X, Y, and Z. But it's not possible because it is what allows us to deal with every project we encounter, every hardware we encounter, and pick the right decision. There's also what I call the "we aren't alone" problem. I don't have a better name, and that's what comes up in my head whenever I think about that. Your boards are pretty complex. So you don't have a single CPU that can make all of the decisions. That's what I'm thinking about. So I've been, as I said, working on a lot of TI platforms, and they have a lot of features that you need to deal with. And they have some more ARM cores that you might need, but all of those could access resources. And so you cannot assume that you have full knowledge of what your hardware should be in, which state it should be in, because maybe someone else needs some part of the hardware. So dealing with power domains in that case is getting complex, because maybe someone else, another CPU on the board requires something inside that power domain. So I'm not saying that this is solved. I'm not giving solutions for that. I just want to list a few things that you need to care about when you think about power management. I hope this is all clear. So let's get started with power management APIs inside the kernel. First off, so this is Runtime PM. We heard that name quite a bit. I hope it is a bit familiar, but I want to recap what it looks like. So at the top, you have your per device APIs. So those are the two function pointers that you implement when you want to do runtime PM. So you have one runtime suspend. So that's when your device is currently being used, but is not used anymore. This function will be called. So the definition is really vague because there's a lot of things that mean that tell you that maybe it will be done later using auto suspend, or it will not be done at all because someone else uses it, or maybe runtime PM is disabled. Yeah, basically something that turns off your device and something that brings it back up, which is runtime resume, that function. So that's all ref count based. It is not something where you do PM runtime enable that will turn on the device. It is ref counting based. That means whenever something needs a device, it increments its usage count, its ref count, and that will maybe turn on the device if this is the switch from 0 to 1. Or the reverse operation, if you go from 1 to 0, then you might turn off the device. So the API, when you consume something, is at the bottom right. You enable or disable runtime PM, and then you get and put whenever you want to make sure that the device, the hardware behind the struck device, is activated. And that might end up calling your runtime suspend, runtime resume. It might not. You do not know. Notice the sync alternatives. Those are when you want to, at the end of the get sync, you know the device is active. Get is asynchronous in a sense where you are not sure, and it might be running the runtime resume function in another thread somewhere else. Something else to care about, you don't only want to enable a single device when you need a struck device, you need to enable its whole parent hierarchy. That's because if it lives on a bus, you might want to turn on the bus. So that's done automatically, but by this, what we call the device model, using the call. So those are kind of recursive, where if you do a PM runtime get, you actually increase the ref count of not only the device that you want, but the devices that are parents to it. So that's what it looks like. I didn't take any code because I don't have much space on the slides. So that's just a dummy example, but it looks really similar to what you could expect. We usually start at the bottom when we talk about drivers. That's much simpler because you start with the platform driver definition at the bottom. So I called it X driver. It gives a probe function and it gives some driver PM callbacks. And then at the bottom you have your macro that defines your driver. We won't talk too much about that. Just above, you have struct dev PM ops. So those are your power management operations. That's the list of operations, and some of those are runtime suspend and runtime resume. There's a lot more to cover. See my first talk if you want to learn about system-wide suspend, and the rest I've not covered too much. But documentation is pretty good in that aspect. So that's what it looks like. And then, of course, you define your function just above. You define them statically, and you do something to turn off or turn on your device. And then in your probe function, what you want to do is make sure that you tell the the runtime PM subsystem that you want to be part of it. So you enable runtime PM for your current device. That tells the runtime PM subsystem that you want to take part in that, and then you maybe get sync to make sure that after the get sync call, while the device is enabled, the hardware is active and you can access it. So that's pretty common inside probe functions. You might do your get sync and then you do accesses to the hardware. You might want to release it at the end once you're done with your probe, and whenever something does an operation on your device, you need to get sync back and put at the end. Or some devices also just get sync inside the probe function. They have the ref count to at least 1 for the whole lifetime. That means it just calls runtime resume at the start and don't do anything else. Okay, so I covered the basic aspects. That is when you have, runtime suspend and runtime resume callbacks. Question is, does it make sense to actually have runtime PM enabled when you don't have callbacks? If you think about it naively, it might make sense indeed, or it might not make sense. But actually, there's a lot more to cover about runtime PM that tells us that actually there is some sense in doing what's on the screen. So you do get sync, and it ends up doing something. So what does it do? Well, we kind of covered the first thing it does is that it makes sure that your parents are active. That's one thing that can be important. You wake up your device parents. So that's it being recursive. There's a few cases where you don't do it. If you want to go and read the runtime PM code, it is readable, but not always straightforward to understand. You have some flags, for example, to ignore your children. I'm not sure, I haven't dig too much into which use cases that could make sense, but if you know you are not dependent on your children, then it could explain that. And your ref count, so that's the dev power usage count, is always incremented. So you always increment the ref count for your parents, even if it doesn't have runtime PM enabled. And if it enables it later down the road, then it will notice that its own ref count is increased, and it will make sure to be active. So let's take an example of a device that does exactly that inside the kernel. So I did not have to look too far. What I wanted is a driver that does runtime PM calls inside its probe or somewhere else, but that doesn't register runtime resume and runtime suspend callbacks. So that's one example. I took DesignWare SPI PCI. So it's a PCI driver that is implementing a SPI controller. So be it. It doesn't have any runtime resume, runtime suspend callbacks. This one is pretty special. It doesn't do the runtime PM calls by itself. It asks its framework to do it for it. So as this is a SPI controller, it will register itself as a SPI controller at the top. So it does SPI alloc host. We don't want to go too much into SPI. And then it sets some flags, and notice the one that is called auto runtime PM equals true. So that tells the SPI subsystem that you want your struct device to be runtime PM get whenever a request comes in. So that's really nice because that's most often what you want to do. Most often, if you are a SPI controller, someone comes in and asks you for a request to be made on the bus. Your first step will often be to runtime PM get. So that's great, so it does it for you and you don't have to litter that inside your code. And then, so it SPI register controller when it's done, that's the whole code, but I skipped a few hundred lines. And then what it does is it finishes by enabling runtime PM, because by default it's disabled, so you must enable it up. And in this case, it also sets up auto suspend. So auto suspend is this feature when you do PM runtime put, so you are done with using the device, the ref count comes back to 0 because you were the last user. It doesn't turn off the device because maybe you have a burst of operations, and if you do have a burst of operation, it's much nicer to not shut off and just do them in a row. But for that, you need to introduce some latency in the suspend call. So that's what the auto-suspend keyword does. Here it's 1000, and of course in the kernel we're not really great at units. I believe it is milliseconds. So let's recap what it does. You have DesignWire's PCI that asks its framework subsystem to do PM runtime get and put automatically on every request that comes in. So this is great because it signals your PCI bus controller that you need to enable the bus or disable the bus. And then it also sets up auto-suspend, which is a feature to minimize the number of suspend resume calls if you get requests that are done in a burst. So we are using Runtime PM, and it's doing exactly what we want for our SPI controller without having any runtime suspend or runtime resume implementation. That's really the best example, best setup. The less code you have inside your driver is the nicer, so that's great. And I just wanted to point out one thing, your device model is recursive. So here I took a pretty straightforward example, but you need to imagine that your bus that you are talking over might be landing on itself another bus. So that's where recursivity is really important. So that's the first reason you want to call your parents up. Second reason I could see is that you want to trigger some other, I call them implicit behaviors. So there are some other things that happen whenever your ref count goes from 0 to 1. And we'll see that. So the feature that is implemented to make sure that not everyone needs to add new code inside the power/runtime.c file. You don't want to add new code every time there's a suspend or resume. You use this feature that is called struct device link to add a new link in between two devices. Pretty straightforward. It has some flags because by default it doesn't do anything with Runtime PM. And one of that flag is called DL flag PM runtime. So it links and makes sure that your auto device, device B, is enabled when device A requires runtime PM to be active. So I gave you an example at the bottom. I took some networking code, which might have been a mistake. Here, what happens is that you have a Mac interface that needs a PHY that comes from another Mac interface. And so you don't have any ways to, you don't want to add a new callback to the Mac interface, please wake up the PHY. So instead, what the subsystem does is add a link in between the two devices. So that second device, the one that provides the PHY, is woken up when you actually need the PHY. That's all done inside the subsystem, so you don't do it inside your PHY drivers, it's done for you. So I try to make a list, which is not really exhaustive. I try to cover every subsystem that uses it, but there are quite a few drivers that use this flag by themselves. So first off, drivers net_phy, they use well, what I just described, Mac linking two Macs together if you are using an external Mac. There's pin control that has a weird feature where it can link consumers of a pin controller to the Runtime PM. I'm not really sure where that makes sense, but it is being used, and I would have to dig deeper to understand why that can make sense. You have PCI, they have an issue where you sometimes have multiple devices, so those are separate struct devices that live on the same PCI bus, but actually you end up noticing that if one of those devices is not enabled, the other one is not active either. So here your parent hierarchy is not saving you because the two devices are not parent one to another. So for that, you add a link in between the device that is quirked that needs to have the device B active. So that's done for a few GPUs. Of course, those are complex devices. Then we have the dev PM field inside the struct device. We'll cover that later. You already know we'll be talking about PM domains. And then you have PM domain, which is called generic PM domain. And so I mainly wanted to cover PM domains because someone on the internet said that he didn't understand GenPD, which is power domains. So I'll explain it nowadays. So power domains for Linux. So first off, it might be a bit pretentious, I'm a bit young to do this kind of jokes maybe. So you have dev PM domain, which is a field inside struct device. It's really old. It's from prior to the Git history. And inside of that, you have some callbacks. So I pointed them out. You have kind of a few structs that are embedded one to another. So dev PM domain. You have the ops, which is the struct dev PM ops, the same thing as you where you register your runtime suspend and runtime resume callbacks inside your device. Here it's inside dev PM domain. So that's the main thing we care about. And then you have a few other callbacks: start, detach, activate, sync, dismiss, and set performance state that we'll talk a little bit afterwards. So what's exactly dev PM domain? So that's when you go into a device and you attach yourself to it. There's a few limitations that you want to care about. So first off, it's a field inside a struct device, but there's a single one, right? So if you can't do it, you can't attach yourself to a device because maybe someone else might want to attach itself to it. So really, it's reserved for some specific use cases. You're not supposed to attach new dev PM domain to any struct device because maybe others would want to do it. So it's not great for that. It's not super straightforward to implement, mainly because it doesn't fit the device model. So as you noticed, there's struct dev PM domain, but that's not a device. That's just some struct that lives somewhere and that you attach inside every device. So there's a few callbacks to implement. It's not really straightforward. It's not fitting the object model, so it's not itself a device. And no device is marked as, you don't have any struct device pointer. So you don't know who's instantiating this dev PM domain. And of course, well, it's not a device. It doesn't fit into any standard setup that we use. It, of course, doesn't fit inside hardware description, that is device trees. So we probably need something better. And for that, you have drivers/PM domain, which is a subsystem. So what it does is basically use the dev PM domain, and it is kind of expected to be the only one to use that. And you go into the PM domain subsystem if you want to create new power management domains. So it's much more recent, 2011, by the maintainer of the power part of the kernel. I won't try pronouncing his name, I'm sorry, but he's really nice. That's what the API looks like if you want to register yourself as a power management domain provider. So, of course, you have something that looks like a register inside your subsystem. Here it's called add provider. And you have two options where one of them is simple. That is when you have a single PM domain for your device tree node. And otherwise, you can provide more than one. The nice thing is with PM domain, you don't expect consumers to do something like genpd get domain or something like that. You just define it inside device tree. So that's really great. That's fitting what you can expect from pin control. You use pin control every day inside your devices, but you don't do any pin control state management inside your driver unless you want to change the state from default to maybe GPIO, that kind of things. So at the top, you have a node that's taken from TISOC. You have K3 PDS for power domains with an S. So that's a power controller. It has a given compatible. And then it has a number of cells. So that's pretty standard. That's whenever you want to manage resources inside the device tree, that's what you do it. The provider gives you a number of cells that you need to pass to it at the top. And then at the bottom, you have so some temp sensor, whatever device that uses a power domain, and you have the p handle K3 PDS, and then two cells as arguments. So in that case, the first one is an index to which PM domain you want, and then it is some flags. So pretty standard stuff. So that's how it looks like, and so notice that the compatible, if you go and have a look, it doesn't have any genpd or PM domain calls. It's all done implicitly. It must, however, do runtime power management calls. So I took some driver, and so for example, this I2C DaVinci controller, it does explicit PM runtime calls just because someone is using power domains. And so you need to do the right calls for the power domains to be activated at the right time. So that's just one example, again, of someone that uses runtime PM without any callbacks. So what's that's a famous domain now. There are two callbacks, power on and power off. So again, a pretty straightforward API when you start thinking about it. So power on, well, you know what it means. You want to power on the domain, and that happens whenever you have the first device that is inside the domain that is registered from device tree. Whenever this one gets its usage count incremented from 0 to 1, that turns on the domain, and it can be shut down whenever all devices inside the domain are shut off. So that's what it looks like. It is attached, well, the domain is a device. So that's the first field you have inside. Then you have the struct dev PM domain. Notice that that domain that we saw from that is inside struct device. So that's what we'll be embedding inside struct device. And then you have your two callbacks. And I missed maybe 50 fields inside this struct. So let's recap to make it clear what the benefits are of using PM domain compared to raw dev PM domain field. So first of all, it's really straightforward to implement. I put a link here. This is one example of a PM domain driver that is pretty straightforward. Well, what can you expect? You have two callbacks, power on, power off. They are implemented however you see it fits. It depends on your hardware. So this one is doing readl, writeL calls. So I kept it simple. And that's pretty much it. And then your consumer inside device tree will be consuming from that. You don't need much more. I didn't allow myself to give an example to the TI SCI one because it does mailbox accesses. So it talks into another device to send a mailbox message. So it's a bit more complex code to read, but it works just as in the same manner. So this fits the object model, the device model. I don't know why I called it object. So you have a provider that is one given device, which is great because it means you can go into sysfs, see who's providing what, get feedback from the PM domain subsystem. That's great. You do it from device tree. You don't have to care from your driver. If the driver supports PM domain, a consumer doesn't know that it supports PM domains. It just does semantic calls to runtime get and runtime put. You only have still one domain per device. So that's still a limitation. You cannot register two domains to a single device. You expect it to be kind of a tree of domains, and inside of that you have a device. A device cannot be shared across two domains. That doesn't exist. But you do have a domain hierarchy that exists. That means you can say, well, some domain has subdomains, and then at the end you have devices. So it's a tree with your leaves being your devices. So Kevin here, he has a series to add better support for domain hierarchy inside the DT, the device tree. What he faced as issues was that, so you have domain hierarchy, which is great. You want to use that because it models your hardware better. But actually, if your firmware provides you with a list of PM domains and doesn't give you a hierarchy, then you are stuck with that. You have a flat linear list, and that doesn't work out too well. So what Kevin does is work around that inside the device tree by registering the hierarchy by himself. And again, great thing with PM domain, you get your PM domain enabled without any runtime suspend and runtime resume implementation. So that's great. They don't have to care. They just need to do, I'm calling them semantic runtime PM calls because more and more, and I'll give you some other hints later, runtime PM is more and more not just calling some runtime resume function at the right time, it's doing more stuff than that. I just wanted to give a list of things. So some features, you have what's called PM clock. So that's a great way to attach clock to a given PM domain. So it will do all the clock prepare enable stuff properly. And so you don't have to have every PM domain driver that re-implements that kind of things. So you can click the link if you want, if that rings a bell and that looks like what your hardware is doing. You have some callbacks if you want to do something special whenever a device is attached to your own domain. So that's when, so ideally your domains contain a lot of devices, so that makes it more, if your hardware is modeled like that. To be honest, most of the drivers that you will look at currently inside the kernel, they have one device per PM domain. But if that defines what the hardware is looking like, then it makes sense. There's active wake up, so that's whenever you have something that is needed for wake up of a system-wide suspend, but that is inside a PM domain. So you don't want to shut off the PM domain before going to suspend, because otherwise then you will never wake up, which isn't great. Right. And then you have RPM always on to make sure that your PM domain is always turned off. I think it is only for broken use cases. We have used it in one broken use case where nothing was consuming the PM domain that we actually wanted to activate. It might be useful for console logging as well in some edge cases. Then we'll cover quickly PM quality of service. So quality of service is about saying what's your expectations for a device. So for the moment, we only talked about suspending and resuming in a straight, well, pretty straightforward manner. If you don't have any user, you shut off. Maybe that's not what you want to do. Maybe you want to think about how long it takes to resume, and if it takes too long, then you don't want to go into suspend. So that's what PMQoS is all about. You set a list of requests, so those are your expectations for maximum resume latency, and then that gives a final value, which is the smallest one. So that's the first field that is called resume latency. I won't cover too much the other ones. Min frec and max frec, those are for CPU frec, which I'm not talking about because this is not per device API. Latency tolerable is an interesting one. It is, again, underdefined in the sense that the value is going to be aggregated into a single latency value, so maybe some amount of microseconds, and that is passed on to the device. And then the device does whatever it wants. So I think mainly Intel are using that for LTR, if that rings a bell to anyone. So it is a way to have standard QoS APIs inside user space pseudo file systems to interact with devices, and they use the value however they see fit. So you add your request using the bottom functions, and then at the end you read the value. So the last call is the one that aggregates the resume latency value into a single value, the smallest one usually. So the values, whatever is the resulting value, if it is 0, then it means you expect your device to resume instantly, which is not possible. Let's not hide that from ourselves. So you never go into runtime suspend. Otherwise, I wrote down a kind of pseudocode of what the actual C code that is much less readable than this one does. So what you do is you take your resume latency, you take your children into account, because let's remember that we are a tree of devices. Then you take your known suspend and resume latencies. So your known resume latency is how long it took in the worst case for you to resume in the past. So you will always do a runtime PM in the first case, and then it will give you a first value. And then if that value is too bad for your request, your expectations, then you might not go back into runtime suspend and runtime resume because you want to resume quicker than that. So yeah, that's your suspend latency is runtime suspend. I want to highlight one thing. Often, when you talk about runtime suspend and runtime resume on platforms that use PM domains, your PM domains will be the biggest time sink. They'll, well, on TI, for example, you need to do a back and forth to another core, you need to use mailbox, that can be quite slow. And so this PMQoS I just mentioned is not enough because it doesn't take into account PM domain power on and off. And so for that, you have, of course, other things. It's called power on latency and power off latency. So it's pretty similar, but it takes into account different things. It needs to check for PM domain subdomains. And it needs to, well, it checks every device that is inside, because if you know the resume latency of each device, then you can sum that up, and that will give you a value that makes sense. So pretty complex stuff, but it does what you expect. When you give a value, it tries to not overreach that value. If the value comes from device tree, this behavior is a bit surprising, so I wanted to mention it. If you give a value, you can give some power on latency and power off latency, then it will trust you with that, and it will not measure the time it took for power on and power off each time. So it will just believe you that power on takes this amount of time, and power off takes this amount of time, and not remeasure that. And I gave you the link to the code, which is kind of readable. Some more features. This is a big list. CPU frag, CPU idle, I didn't want to cover because this is not a per device thing. There's a great talk, CPU idle, from Dhruva and Kevin that was done on Monday. So you know my slides were done since then. You also have PM domains that are OPP, so that's whenever you want to do throttling on your frequency and voltage. So if you care about that kind of things, go and check out grep for OPP inside the kernel, and you have the documentation link contributed by TI a few years ago. Hardware mode, that's when you want to do PM that is defined by the hardware. So the hardware defines when you go into suspend and resume. So that can be helpful for some, apparently only to Qualcomm. Stephen Boyd, the clock subsystem maintainer, gave a great talk last year at ELC where he mentioned what he wants to do, that is piggyback more on the Runtime PM features to get all of the SOC-specific code out of drivers and into something that is more SOC-specific, so that the Runtime PM will involve waking up the device in the right manner. Go and watch the talk. It's 40 minutes. I can sum it up shorter than that. Thank you, and if you have any questions, I think it will be in the hallway because we are 41 minutes into it. Thank you, everyone.